Hello. Today we'll be talking about quantifiers and predicates. That is, you'll be, in the words of Obi-Wan Kenobi, taking your first step into a larger world. So far we've spent all this time learning about S and learning about all the connectives, the and, or, if, then, not, etc. And we've been putting whole sentences into little symbols, little propositional variables. And that's a great start, but really there's ever so much more. And the reason we taught US was that so that we could, teach you some other things as well. Uh, Logician E.J. Lemmon writes in one of his sort of famous textbooks about symbolic logic. He says, at this point in the course, when it's time to stop using S and start using what we're going to call P, he says, our ambition is to state exactly the conditions of valid argumentation. To inspire the reader with the correct degree of humility, it is now time to see how very little we have so far achieved. And so then he gives an example very much like this one. Consider the argument, Tweety is a canary, and no canaries are migratory. Therefore, Tweety is not migratory. Has that in common with coconuts. Coconuts are also not migratory. So, clearly a valid argument if you want to look at it. If Tweety's a canary and no canaries are migratory, then Tweety cannot be migratory. Very clear. It's as valid as anything is. So, great. And so in language S, consider symbolizing this, right? Tweety is a canary. That's one sentence. That's one proposition. And so it's just going to be something like P, or, we could give it a letter C to stand for something. I would say no canaries are migratory. Okay, that's another single proposition, right? So, Q or something like that. And then, of course, therefore, Tweety is not migratory. So it is not the case that Tweety is migratory. So simple negation. So it looks like what we're saying here is that C and M as statements entail not T. All right, well, again, the argument looks as valid as anything, and so S should tell us this argument is valid, right? Anybody here want to try the proof, right, to show that so again, we set it up and say, okay, let's see, we want to get not T, right? Maybe our first step is to assume T, right? For reductio, and oh, we need a contradiction, and there aren't even any connectives, right? So looks like we're sort of host. But again, remember, a proof isn't diagnostic. A proof isn't going to tell you whether something really does or doesn't entail something else. But if it does entail something else, you can then eventually prove it. So if your proof isn't working out, one of two things is true. Either it can't work out, or you're just not doing it right. Well, let's maybe think maybe we're not doing this proof right, although again, it looks like there's no possible way for this thing to work out. Let's, try maybe look at it on a tree or a truth table. So here's the truth table, okay? We have, C and M and T here, and then of course we have not T. As it's a pretty simple truth table. So let's mark our first premise, which is C here. Our second premise of the argument is going to be M. So we'll mark that. The conclusion is not T. So we'll mark that. And now again, remember how to check validity on a truth table. You look for any possible line where the premises are all true and yet the conclusion is false. And looky there. We have that right on the first line of the proof, showing very clearly this is invalid in S. Well, that's unfortunate. And so it looks like we have an argument that is valid as the day is long, and S is telling us it's not valid. This is bad. Okay. All right. So you've reached the I told you that story to tell you this one section of the course. I'm not really sure that I've actually said that you can do like every possible, everything you can say in natural language you can say in S. I'm not sure I've said that, but I'm pretty sure I've implied it. So that's just it's not true. It was fine to think it was true for a while, and that has its uses, but of course it's not true, as we just saw with the Tweety example. So what now? All right, and why did we bother with S if we're just going to move on to P? Well, we'll answer all those questions. Oh, okay. Well, I just said that. I guess I could have just advanced. Okay, there we go. Now, this again, this isn't as bad as it looks. Everything that is true of S really is true of S, right? S really is very useful for all kinds of arguments. Um, there's all kinds of things you really can use S to analyze perfectly, right? And if you don't need anything more complicated than S, you'd be silly to use anything but S, right? So everything's still good. It's not like you have to like throw away or ignore anything else or anything like that. It's just there's just more. We can make our system slightly more complicated and much more powerful. And so what we're going to do here is we're going to start introducing the notion of predicates. This idea that there's more structure in a proposition that we can represent, and that sometimes collections of claims have interesting properties based on the structure inside the proposition rather than just how the propositions are related to each other. So language S tracks how propositions are related to each other. Language P, is what we're going to call the language we're going to learn now, will track not only how propositions are related to each other, but how certain elements of propositions within propositions are related to each other. Sentential logic, that's what language S is for, or S for something you could call S for symbolic logic, whatever. But that deals with whole propositions, right? So a whole proposition is P, a whole proposition is Q, etc. Predicate logic, which is we're going to introduce here, called language P, it's a little more fine-grained. Okay, it's going to split the logical subject from the logical predicate. So I would very strongly advise taking a look at the section of the text that deals with this. For P, right, in language P, we're going to represent predicates, that is properties of things, with capital letters A, B, C, etc. And we're going to represent individuals with lowercase letters. This is a little bit counterintuitive, but it's the way it's always been done. We tend to think of, like, if we want to say, like, Bob is a villain or something like that, we're going to use a capital V to indicate the predicate is a villain. And we're going to use the lowercase b to represent Bob, even though we'd capitalize the proper name Bob or something like that. So, again, slightly counterintuitive, but this is just the way it's always done. And so here are some examples of predicates and some predicate language. You'll again see it's not that much more complicated than S. So if we're looking at the statement Socrates is mortal, okay, what you're going to do is you're going to represent the one place predicate is mortal with the capital M, and you're going to represent Socrates, who is an individual, with a lowercase s. Right, and so saying, instead of just saying P, like you'd say in language S, you're going to say M, capital M, lowercase s, and that's going to be Socrates is mortal. Okay, and so you might say something like predicate is mortal, subject Socrates. Right, that's the idea. You could say Napoleon was Chinese. Of course he wasn't, but you could say he was. And if you're going to say that in symbolic language P, you would simply say, the predicate was Chinese, right, is going to be symbolized by the capital letter C. And Napoleon, an individual, is symbolized by the lowercase letter n. So CN is Napoleon was Chinese. Okay. Notice we also have a very expansive idea of what counts as an individual. Okay, so we don't necessarily mean a proper noun like a proper person, place, or thing. We mean anything that you can say something about. And because you can say something about courage, right? Courage can have properties. It can be an individual in a claim like this. So you want to say courage is desirable. The sentence is about courage, right? As a thing, right? You might say something like communism is unjust, right? Well, communism is a thing in that sense. Okay, so the word thing is going to get pretty expansively used here. And so again, we say the predicate is desirable is capital letter D, and courage is as a thing, okay, is our lowercase c. If we want to say something like, sometimes predicates have more than one place in them. Okay, so we might say something like Biff punched Chuck. In this sentence, we have two individuals. We have Biff and we have Chuck. And so we can use the capital letter P to stand for the two-place predicate blank pinched blank, right? And notice we can get around various different ways of expressing the same English sentence, and use a little bit of judgment here. So if you later see the sentence Chuck was pinched by Biff, right? You can just symbolize that the same way. Again, this is blank pinched blank, and it's Biff who pinched Chuck, right? If Chuck was pinched by Biff. So you can use a little judgment there. Recognizing that these two things really do express the same proposition, even though they are different English sentences. And this is a little bit of explanation on what I think too briefly perhaps mentioned in the text when I went over it. In this sentence here, let me get my little pen out. So this sentence here, right, where Biff punched Chuck, Biff here is the grammatical subject of the sentence, and then pinched Chuck is the grammatical predicate of the sentence, right? Well, in terms of logic, though, we have two things. We have different things in mind. We have Biff is an individual and Chuck is an individual, and we have this blank, blank pinched blank, right? That's actually that's a logical predicate. And so there's a difference between a grammatical predicate and a logical predicate. Likewise, in this sentence here, Chuck is the grammatical subject and was pinched by Biff is the grammatical predicate. But again, in logic, what we have is here is Chuck is an individual, Biff is an individual, and then we have this, sort of was pinched by business that takes, two particular places, right? So that's some of the difference between a logical predicate and a grammatical predicate. Use the same term and they're sort of, kind of similar in concept. They're not the exact same thing. All right, so the purpose for learning language S is twofold. Again, you might very well wonder, why did we bother with S if we're going to just add this stuff later? Because it's much easier just to add this little wrinkle than it is to teach it from scratch this way. Because it's just, for a number of reasons. And we'll get to some of those here. So number one, look, lots of claims and arguments, lots and lots and lots of claims and arguments really can be analyzed using S, right? S is quite versatile. It works very well. And that hasn't changed. It's just that it doesn't work for everything. And we have a more powerful system available. Also, the operators, that is the negation symbol, the syntax, like the rules for how you put things together, the quantifiers, or not the quantifier, the connectives like and or, and the conditional, the biconditional, all that stuff works exactly the same as P as it does in S. And so if you learn how it works in S, you know it, and you don't have to learn anything new to operate with those same symbols in P. So again, S makes the learning of all those symbols and everything much, much easier. And so, for example, if you wanted to say something like Napoleon is not Chinese, right, it's going to be just the same thing as before. Whereas before in S, Napoleon is Chinese is just P, and then Napoleon is not Chinese is just not P, right? Well, here, if Napoleon is Chinese is capital C lowercase n, then not capital C lowercase n is Napoleon is not Chinese, or it is not the case that Napoleon is Chinese. No problem. Okay. If we want to say Socrates and Aristotle were Greek, well, we say Socrates was Greek and Aristotle was Greek. We say, G, capital G lowercase s, and capital G lowercase a, right? Socrates is the S, Aristotle is the A, blank is Greek, is our predicate G. Simple enough, okay? So all of that stuff is exactly the same. You don't have to forget about any of that. Here's the other thing, though, and I guess I'd forgotten to note it on this slide, but I'll mention it now. Truth tables work great in S. They don't work very well in P. In fact, don't really work at all in P. Proofs are pretty easy in S. They're a little harder in P. Okay. Trees work exactly the same in S and P, except for a couple of rules we're going to add to them. And so learning all that stuff with respect to S, learns some really important things that to some extent don't work very well in language P. And it's good to learn those things. Okay, so here's the other thing we're adding, right? So the difference between S and P is not just that P has predicates, although that's a big difference. The other difference is that we're going to add a couple of operators here called quantifiers. And so I want to motivate why we're doing this way. Okay, so imagine saying something like if you, ordinary English sentences quantify things all the time. They say stuff about all things, about no things, etc. And so imagine saying something like all of the Stooges were men. Of course, here referring to the three Stooges. Um, and, uh, uh, and so here's how we would put this into language P. Okay, we would say that Larry is a man. So I'm using the capital letter M for the predicate blank is a man, right? Or was a man. We could say either. It doesn't matter. And so L is the individual Larry, right? And C is the individual Curly, and M is the individual Mo. Now, of course, I understand if you're sort of a stooge purist, if you want to say that that Shemp was rather, sort of predated Curly, and you think that he should be added in here, that's fine. If you liked some of the Joe Besser stuff, or the later sort of Curly Joe stuff, whatever. I mean, pick the lineup you like and use the capital letter you like. I'm using sort of more or less, I think, the most iconic representation of the Stooges. There were, a total of sort of 6 Stooges, but of course Larry and Moe being the consistent ones all the way through. And I guess 7 if you count Fake Shemp, whatever. So again, if you're going to say something like all the Stooges were men, you have to account for all the Stooges. And I guess if you wanted to account for all 7, including Fake Shemp, or 6, not including Fake Shemp, you'd have to just sort of add more ands here. Okay, but the idea is that if you want to say all of the Stooges were men, you have to name every Stooge and say this one's a man, that one's a man, that one's a man, that one's a man, until you hit all of them, and then that's how you can say in language P that all of the Stooges were men. Okay, that's a little clumsy, right? I mean, thankfully that there are canonically 3 Stooges, right? Now, of course, some of the Stooges you want to say some of the Stooges had curly hair, which actually no, but if you really want to put that there, some of the Stooges had curly hair, right? So, in order to say that in our language P, think about it for a second, see if you can anticipate me here. You want to say either Larry has curly hair, or right, Curly has curly hair, right, which is the joke, or Mo has curly hair, right? Or until you're out of Stooges, okay? And then once you're out of Stooges, you have said at least some, that means at least one of the Stooges had curly hair, possibly more than one. So you use a disjunction for that. If you want to say none of the Stooges were smart, right, which is kind of the joke, I guess, then you want to say, well, Larry was not smart. It isn't, or rather, it is not the case that Larry is smart, right? And it is not the case that Curly is smart, and it is not the case that Mo is smart, and until you run out of Stooges. Okay, some of the Stooges weren't bald. Okay, that means that you say Larry was not bald, Curly was not bald, Mo was not bald, right, etc. Right? You want to say or until you run out of Stooges. So this all works fine if we're dealing with relatively small sets of things, but now consider trying something else. Try all crows are black, okay? Now forget, like, the crows don't have names. Let's just number them. Okay, crow number 1 is black, and crow number 2 is black, and crow number 3 is black, and crow number... And so you're gonna end up writing that out until you end up, at the end of all crows. And the crows, like a single crow's lifetime is not enough for you to write down all of that. So this is a problem. So you have to say, this crow is black, and that crow is black, and the third crow is black, right? So the way that sometimes philosophers or logicians will write something like that is to use this little thing here. This is called a prime. Okay, and so you want to say C, the crow number 1 is black, crow prime is black, and then the third one would be like crow, and what they do is they'd add another one. Crow prime is black, and crow prime is black. We'll get to more of that sort of later in the text. We'll be utilizing some of that notation, but for now it doesn't really matter. The idea is this, that if this is how you're going to try and say something like all crows are black, that's really clumsy, and you're going to run out of ink and paper and not be able to say anything productive. So really we want more productive ways to do this. Likewise, if you're going to say something like some bands suck, right? You could, like Limp Bizkit, for example, they suck. So if you say yes, this band sucks, or this other band sucks, or until you run out of bands, and of course, that's not practical. So we want a different way to handle quantification, different ways of saying like all or some or none, etc. And so you might have noticed that sentences involving quantity terms like some involved strings of disjunctions, and that sentences involving quantity terms like all or every involved strings of conjunctions, right? Same with none, like negated, etc. And so to abbreviate all this awkwardness, what we're going to introduce is two new symbols to our language P that will allow us to use universal quantity terms like all or none and particular quantity terms like some a little bit more economically than these strings of conjunctions and strings of disjunctions. So I want to first talk to you about this universal quantifier. This here is what it looks like. Okay, that's the universal quantifier. It's in parentheses an upside down A next to an X. Now that X can change. That you can have various different letters in there, but often enough you'll see it with an X. And so it's an operator, okay? So it works in terms of scope the same way that a negation works, right? What's in its scope is whatever is immediately to its right. Or, well, to your right when you're looking at it. That's its right. You know, it's not. Anyway. So it's used whenever you want to quantify over a whole class of things. That is, whenever you're using words like all or every or only, etc. Okay? Those sorts of things, as well as sort of none, but you'll have to modify it for that. And so when you're reading this in logic, right, when you're reading from logic into English, from language P into English anyway, I want you to, when you see a symbol that says that, use the words for all of X, okay? So if the capital letter P stands for the predicate blank likes pi, right, then the sentence in P that we see written here it should be read in English as for all of X, okay, that's this part here, X likes pi. Okay, so you read this for all of X, X likes pi. All right. And of course, if you write, you know, this for all of X, X likes pi, that means everyone likes pi. Right, for all of X, X likes pi. Everyone likes pi. That's what that means. And so if you want to say all people like pi, you want to say for all of X, X likes pi. That's how we do that. Instead of saying you like pi and you like pi and you like pi and you like pi and you until you run out of people, right? That's this is much better. Likewise, if we want to use the talk about some things, right? You know, what we use is this existential quantifier, okay? And that's again, this backwards E. And again, why? Just so that we don't get it confused with our regular like capital letters for some reason, you know, and think it's just another predicate. I guess that's why. But these symbols are pretty much universal. So in terms of like everybody uses these for quantifiers. So again, we have this little backwards E and the X, and this this thing here is the existential quantifier. Again, it's also an operator, just like the universal quantifier. Its scope works just like the negation. And we're going to use that operator whenever one wishes to quantify over particular things. That is, when we're using the words like some or someone or at least one or something like that. That's what we're going to try and do there. So this symbol is most straightforwardly read in English as there exists an X or there is an X such that ... right? So again, if the capital letter P stands for the predicate likes pi, then the sentence in P that looks like this one here should be read in English as there is an X such that X likes pi, or there exists an X such that X likes pi. Okay, that's what it's. There exists an X such that X likes pi. And that means, intuitively, like in more common English, somebody likes pi. Right? There exists an X, and X likes pi. Somebody does. We don't really have to care who. So notice what this does is it allows us to say something about an indefinite individual, right? You can say Bob likes pi, in which case you would just say capital P, lowercase b. Bob likes pi. But if you just want to say, well, somebody likes pi, right? This is how you do it. You just say, well, there's just some X. And that X likes pi. All right, so let's take this moment to update our syntax rules, the rules for how to put together, you know, well-formed formulae, you know, proper expressions in language P. And you'll notice that these look a lot like the syntax for language S. In fact, there's only really one change. And so syntax rule is, well, two changes, I guess. Rule number one is the rule for what we call atomic sentences. These are the sentences that we sort of build other things up out of. So an atomic sentence is a capital letter accompanied by one or more lowercase letters. So, capital F, lowercase p, say Paul is funny, a lowercase q with a capital G. Oh, wow. Quentin is great, right? Or a relation, right? So a two-place predicate. So like Rob hates Sam, or whatever. It doesn't. So and again, you can have a three-place predicate, a four-place predicate, a five-place predicate. There's no limit on the number of places that could go in a predicate. Most of the time, you're going to see 1, 2, 3, etc. And so again, any of these things, any capital letter with some number of lowercase letters after it is a well-formed formula. Okay, so that's good. That replaces the old syntax rule, which just says that a lowercase letter is a well-formed formula. So that's one difference between the syntax of P and the syntax of S. And so this is the other difference, is syntax rule 2. This is the rule for operators, because we're adding a couple of operators. Okay, so any operator, okay, the rule goes this way, an operator, which is the negation, or the universal quantifier, or the existential quantifier, okay, that's the negation, the universal quantifier, and the existential quantifier. Any of those with a well-formed formula in its scope that is to its right is a well-formed formula. If the operator is a quantifier, it must have, so that is one of these two things, the universal or the existential. If the operator is a quantifier, it must have a lowercase letter next to it that is contained in the sentence that is in its scope. Okay. So for example, if you say something like, for all of x, b, capital B, lowercase s, that's going to be improper. That's not going to follow syntax rule number 2, because here we have this universal quantifier that has a lowercase letter to it, but that lowercase letter isn't found in the sentence that is to its scope. Now, if you want to say, b, s, x, so you want to say for all of x, s bears the b relation to x, right? That's effectively what's going on there. Like give an English sentence. So for all of x, Sam beats x, right, at Monopoly or something like that, right? So Sam, what you're saying is Sam beats everybody at Monopoly. Okay, that's that's what's going on in a sentence like that. Okay, but that's that's the only other difference. You'll notice syntax rule 3 is exactly the same in P as it is in S, which is again one of the reasons for learning S first. It's a little simpler. So this is the rule for connectives. That is a connective and, or, if then, if and only if, with two well-formed formulas in its scope, that is one to its left, one to its right, is a well-formed formula. Same thing as ever. And so if we have, something like, again, B, capital B, lowercase s, and capital P, lowercase v, right? Again, if this little bit here is a well-formed formula according to rule 1, this here is a well-formed formula according to rule 1, and so then the whole thing with a little and between it is a well-formed formula according to rule 3. So so that works exactly the same as in S. We're just using different atomic statements, and we're adding this quantifier business. And then, of course, syntax rule 4 is exactly the same. It says anything that can be generated following the iterations of rules 1 through 3 is a well-formed formula. So again, this helps you follow the rules, and the rules are put here for a reason. If it violates the rules of syntax of P, there's not going to be a sensible English sentence that actually gets symbolized by that. And so these rules help you from not symbolizing things into nonsense. So pay very close attention to these rules and do know them well. All right, finally, I want to, well, not finally, but next, right, I want to talk about quantifiers and negations. Okay, that is because sometimes this this one really gets people, and it's one of the first things to sort of really walk through. And so if you're not careful here, you're generally going to get stuff wrong. And as usual, the most important way to keep yourself from getting it wrong is to keep the connection with natural language. Again, this is just shorthand. This is, we're not inventing an entirely new language that has a whole new vocabulary or whatever. We're just using some symbols so that we can see the structure of the language we already have. And so, for example, all and none seem to be opposites, right? If it's sort of opposite day, and instead of saying all the people in the class are nice, you would say none of the people in the class are nice, right? Something like that. And so it's easy to think that it is not the case that for all of x means something like none, right? So if for all of x means something like all, then not for all of x means something like none. That's a very easy thing to think, but it's a mistake, okay? And so if you consider the phrase everything is awesome without getting any silly tunes in your head, try that. That's a challenge. It can be expressed as with this expression right here. And again, this says for all of x, x is awesome. Okay, so that's everything is awesome, right? And I did just the right cadence on that. Now you've got the tune in your head. I'm sorry. Okay, so consider what happens. Now consider what happens if we put a negation on that. It is not the case that for all of x, x is awesome. Okay, right? Again, so it is not the case that for all of x, x is awesome. Another way to put that is not all x is awesome. Not everything is awesome. Now, does that mean nothing is awesome? Not quite, right? That's not the same. Saying not everything is awesome means that at least some things, it implies at least that some things are awesome. So it doesn't mean that nothing is awesome. It just means that not everything is awesome. Those are two different things. Okay, so you have to keep, there's a difference between everything is awesome, not everything is awesome, and nothing is awesome. And not nothing is awesome, right? I mean, those are all different. So in order to see this, what I want to do is show you how negations work with all these things here. And so again, if we're talking about the capital letter P being, I think I'm stuck with likes pi here. If you look at that top line there, for all of x, x likes pi. That means everyone likes pi. And then that second one we've covered, there exists an x such that x likes pi. That means somebody likes pi. Okay, so everyone likes pi, someone likes pi. Great. If we look at these next two, we want to say this, again, it is not the case that for all of x, x likes pi. That means not everyone likes pi. That means someone doesn't, okay? And then it is not the case that there exists an x such that x likes pi. That is actually what means nobody likes pi. It is not the case that there exists an x such that x likes pi. Okay, that is no one likes pi. This next one down, let's see, I'm gonna here we go, laser pointer, right? This one here, because I want to gesture at it, but I don't want to mark it up all crazy. So if we say like for all of x, it is not the case that x likes pi. Okay, that one says essentially no one. That one says no one likes pi. Okay, so it is for everybody. It is the case that x does not like pi. So for every x, x does not like pi. That means no one likes pi. If you want to say just there exists an x that doesn't like pi, that's just somebody doesn't like pi. Okay. So this one again is no one likes pi. This one is someone doesn't like pi. Now you'll notice that these two here are equivalent to each other, and that's going to be an important thing that we're going to be pointing out in a little bit here. Someone doesn't like pi. Also notice this one here and this one here are equivalent to each other. Okay, and so if you sort of stare at that and ponder it for a while, you could even pause the video and ponder it for a while, you'll start to see what's really equivalent to what in terms of these universal and particular quantifiers. But then finally, these last two here, so if we want to say it is not the case that for all of x, x doesn't like pi. So that says not everybody doesn't like pi. And when you twist your brain around a little bit, you think, okay, what that means is that somebody likes pi. Okay, and if you say it is not the case that there exists an x, that is, there does not exist an x that doesn't like pi. They say, well, there's not anybody who doesn't like pi, right? Which means everyone likes pi. And again, you'll notice that this one here is equivalent to this one here, and this one here is equivalent to this one here. So take this here being equivalent to that, and that here being equivalent to this. We'll just put that on the next slide. Okay, and so what we're seeing here is that not universal not is equivalent to the particular, and that not particular not is equivalent to the universal. So that's actually how the negations end up working out there. And it's worth it. When you start out, you're just going to have to read it out into English and think about it until you start getting used to the way this works and really internalize the operations of these things. So I want to talk about how we can start to use this in terms of some practical sentences, right? And so we very often in any natural language, English included, we'll talk about things either sharing or not sharing properties. So often we'll want to say things like, all Greeks wore tunics, right? Or no Greeks wore togas, because that's actually true. It's one of the things that drives me absolutely insane about movies and about popular culture, where like if you go to like a sorority or fraternity party, right, which is no like Greek society, everyone's like wearing togas and stuff, and like togas were Roman garb, not Greek. It's again, drives me crazy. So in any case, yeah, no Greeks wore togas. Romans wore togas. Greeks wore tunics. Okay, um, at least Greek men did, right? I'm not sure if there was a name for Greek women's garb. That I wouldn't have put it past the Greeks not even to have a name for women's garb. So little did they think of women, at least in the ancient world. Not, I can't say anything about modern Greeks. Um, yeah, anyway, so again, we're trying to say, yeah, the Greeks have this property that they wore tunics, and they have this property that they didn't wear togas, right? Or we want to say that some cats have the property of looking like they're wearing socks. Okay, some do. My cat, for example, does look like he's wearing socks. Some cats do not look like they are wearing socks, right? This is a thing you can do. Actually, you can sort of mock your cat a little bit. So if your cat does look like they're wearing socks, you can, while folding laundry or whatever, put some socks on, just sort of look at them the way they're staring at you, and just, they don't get you're mocking them. It's sort of fun in a way. I don't, the fun doesn't last that long, but it does last. And so anyway, we can just say that the point is that our quantifiers plus the familiar connectives and operators can express these propositions. Okay, and I'm going to show you how that goes. So when we say for every x, if it was Greek, then it wore a tunic, right? So that's how effectively in logic speak, how we're going to phrase the common phrase, all Greeks wore tunics. And so we use the universal quantifier here for all of x. If x is Greek, then x wears a tunic. Oh, I'm sorry, I didn't change that from a previous format. So yeah, pretend that's a horseshoe. Yay! Right. In fact, let's just yeah, I'm gonna. Oh, I don't think I can do it. Yeah, that's really tiny, but hey, that's not too terribly bad. It's also a white cursor, so I can't really exactly see where it is, and so this is going to get harder and harder. But yeah, you can barely see that anymore. Now, yeah, we're just gonna there. Oh boy, isn't that a great drawing? That's perfect. Okay, um, very silly. Okay, so and I've got the same problem here, but I'm not going to worry about it. Okay, so the sentence "No Greeks wore togas." Okay, again, remember that all and none are not just intuitive truth functional opposites. And so what we're going to say in logic speak is for all things, if it was a Greek, right, for all of x, if x was Greek, right, then it did not wear a toga. And so we're just going to negate the consequent of the conditional there. So when we say for all of x, if x was Greek, then it is not the case that x wore a toga. Right? That's no Greeks wore togas. Want to say some cats look like they are wearing socks. Okay, what we're saying when we say that is that there exists a thing, and that thing is a cat, and it looks like it's wearing socks. And so we're essentially saying two things, right, about an object. We're saying there exists some x, and that x is a cat, and that x looks like it's wearing socks. Okay, that's how we say some cats look like they're wearing socks, without necessarily pointing to a particular one. Right? If we want to say that Ludwig the cat, which is my cat, looks like he is wearing socks, we would just say capital C lowercase l, L for Ludwig, and capital S lowercase l. So Ludwig is a cat, and Ludwig looks like he is wearing socks, right? So we want to say yeah, etc. But yeah, if we just want to say some cat, right, we have to use the existential quantifier. And again, if we want to say some cats do not look like they're wearing socks, we throw in a negation, not at the beginning, right, but here in the nuts and bolts, in the guts of the sentence here, right? Because what we're saying is there exists an x, okay, and that x is a cat, and that it is not the case that x looks like x is wearing socks, or looks like it is wearing socks, right? So that's how you do some things like that. In fact, this way of talking about or doing logic is the oldest way of doing logic that we have in the Western world, and really, the world in general. this is the system that Aristotle came up with, right? He thought, you know, you can really break down all claims into what he called A, E, I, and O claims, right? These are sort of really the first four sort of vowels in Greek, and so they're transliterated in English, and so yeah, the idea is that they're just sort of called that. There's no reason. The reasons why they're called A, E, I, and O claims are now kind of obscure. Um, there's no handy mnemonic for that. Just A, E, I, and O. And what Aristotle said was you can break down basically all assertions into collections of A, E, I, and O claims, right? And from there you can arrange them into some very strictly structured argument structures, and then that are called syllogisms. You can sort of look this up if you're really interested, or ask me about it, and I'll tell you all about it. But we don't have to worry about that now. But whenever you are saying something about something being in some other category or something not being in some other category, it's useful to know these because they help you formalize ordinary language, because ordinary language does contain a lot of categorical claims like this, like these A, E, I, and O claims. And so the A claim is the claim that all of one thing is another thing, right? So all A are B. So like all dogs are mammals, all men are mortal, all et cetera, et cetera. So that's the idea, is that all A's are B's, right? It says all A's are in the category of B. And the way you say that in our language P is to say, well, for all of Y, and now notice you can use X here, you can use Y, you could use A, you could use B, you can use any letter you want, as long as the letter that we're arranging over here is saying for all of Y, okay, A is the Y has to be somewhere in the scope of the thing too. So so for all of Y, if Y is an A, then Y is a B. Right? That's how we say that. That's the claim. All A's are B's. So all dogs are mammals, right? If Y is a dog, then Y is a mammal for all Y. The E claim is also called the universal negative claim. The A claim is a universal affirmative claim. The universal negative claim, no A's are B's. This is to say there's no overlap between two categories, okay? You want to say something like no reptiles are mammals, okay? The way you say that, you say, look, for all of Y, if A is a Y, then it is not the case that Y is a B, right? So if it's a reptile, then it's not a mammal, or if it's a mammal, then it's not a reptile. Either way, those statements are actually equivalent, right? That no mammals are reptiles and no reptiles are mammals, totally equivalent. Although A claims don't convert like that. It's what we call conversion. The I claim is that some A's are B's, that there's some overlap between two categories. All right, and the way we say that is we say there exists a Y such that Y is an A and Y is a B. All right, you want to say some good drivers are middle-aged, right? So you want to say some middle-aged people are good drivers. Either way. Right? If you want to exclude something from a category, you want to say no whole grain breads are tasty breads, or something like that, right? Well, no, that would be an E claim. So you want to say that some whole grain breads are not tasty. Make a sort of claim. So the idea is that you want to say there exists a Y such that Y is an A and it's not a B. So Y is a whole grain bread and it's not tasty, right? Or something like that. So some A's are not B's is an O claim, and that's what it looks like in our language P. And so I would probably get really familiar with these, maybe even just flashcard them out, because it makes it a lot easier to formalize a lot of ordinary English claims, because these kinds of claims, all A's are B's, no A's are B's, some A's are B's, and some A's are not B's, they're just so common in ordinary language that this is a handy little sort of shortcut to help you. So now we're going to take a look at some of the ways in which our formalization can get a little bit tricky. Okay, and so imagine we have a sentence something like this one. We say Jane is looking for a perfect dress. Right. This is a little bit like the sentence, like Columbus is looking for a safe harbor, or I think in the text I said something about somebody looking for a chupacabra. Right. The idea is that sometimes when we talk about things that don't exist. Right. So when you tell a child there's no monster in your closet, right? You're not saying, look, there are monsters. It's just that there isn't one in your closet, right? That's not exactly what we're saying. We're talking about monsters, but we know they don't exist. And so talking about things that don't exist is a little bit interesting, because we want to make sure that you don't formalize something in such a way that gets across meaning that you don't intend. Right. So for example, if we take the sentence, Jane is looking for a perfect dress, it would be very tempting. Well, of course, we have to specify our predicates and our. So this is when you're formalizing. This is just good practice. Write down what your capital letters actually stand for. Write down what your lowercase letters stand for, and then you write down your actual symbolization. So this is a little more involved than formalization that we saw with language S, but it pays dividends to just write it all out. It makes things so much simpler. And so capital letter L is going to be blank is looking for blank. Okay, it's going to be a two-place predicate. So if Biff is looking for Chuck, we have capital L, lowercase b, lowercase c, right? Biff is looking for Chuck, right? D, right? The capital letter D is going to be blank is a perfect dress, okay? And then, of course, Jane is the only individual we need in this sentence, and so we're just going to use the lowercase j. And so, given all that, it would be very tempting to write there exists an X such that there exists a thing, right? There's something, and it's a perfect dress, and Jane is looking for it, right? So yeah, there exists an X. X is a perfect dress, and Jane is looking for it. All right. But notice that's a lot like saying there exists a thing, that thing is a monster, and that thing is not in your closet. Right? So that's like telling a kid, and it's like, oh no, there are monsters, right? There's just not one in your closet. That's not what you meant, right? And we don't mean to say that there really is a perfect dress out there, and Jane is looking for it, whatever it is. We want to acknowledge the possibility that there may be no perfect dress out there, okay? And so instead, what we want is to say we want to use a conditional here. Right, the conditional is really what makes this whole thing go. We want to say, because when we say if one thing, then another, we're not actually committing ourselves to the existence of either one. I would say, if a giant nerve gas farting dragon swooped down upon us, then we would all be dead. No, I can say that without committing myself to the existence of giant nerve gas farting dragons. Okay. That's that's one of the great things about a conditional. And so that's what we're going to do here. We're going to say, look, for all of X, if X is a perfect address, then Jane is looking for it. Right? That doesn't mean it exists, but it does mean that Jane is looking for a perfect dress. Okay. And so this is a little complicated because sometimes we want to, if we're talking about something that we want to acknowledge the possibility it doesn't exist, it should be in a conditional, right? This thing that may not exist. Another tricky situation sometimes we can get into, and this is, again, with slightly more advanced formalization, is when we have to use more than one quantifier. Okay, so if you look at the sentence, there's someone out there for everyone. Okay, that's a nice sentiment anyway, right? So someone, okay, that's a quantified phrase. That's a phrase that sticks out. Says, hey, quantifier here, right? So someone, whenever you see someone in a sentence, you're like, oh, that's a quantifier. Okay, so somebody. Okay, that's there's somebody out there. That's and probably an existential quantifier. You want to say there exists a person out there, right? That sounds like there's someone out there, right? So that's an existential. And then we say everyone. Okay, that's universal. Okay, that's a universal quantifier there. So there exists someone out there for all of X, right? There exists an X out there for all of X, right? So there's someone out there for everyone. And so the reason this is tricky is because sometimes you have to really think carefully about the order of these quantifiers. And so here, when we're formalizing this, we want to say our capital letter F is blank is for blank, right? So someone is for someone else, right? That's the idea. There's someone out there for everyone. So that's the only predicate we really need. Notice this sentence doesn't name any specific individuals, right? Any things, right? The thing that the grammatical subject of this sentence is someone, right? Or rather, there is, right? That's, again, nobody's named. So we don't have any individuals named in the sentence. We're just quantifying over somebody or everybody or whatever. We're quantifying over indefinites. And also we want to add in this bit here that we're having a universe of discourse, right? And what this does is it helps us to make our statements a lot more simple, right? And so if I hand you like a bag of marbles and you say, oh, what color are these? And I say, oh, they're all blue. you understand that I mean out of all the marbles that are in that bag, they are all blue, right? But if you just say something, if you just write down, say for all of x, right? If you just write that down, if you write for all of x, x is blue, right? Notice without a limited universe of discourse, that says literally everything is blue. So when I say they're all blue, you could sort of symbolize it this way, but without limiting the universe of discourse, I'm really saying everything's blue, not just the marbles in the bag. And so again, when I hand you a bag of marbles, say, oh, they're all blue. They're all blue ones in there, right? So that's what. So when we limit our universe of discourse to people, when we say something like for all of x, x is x is a b. So b, let's say, is boring, right? That says everybody is boring, not everything in the universe is boring, right? So we're limiting our universe of discourse a little bit. So since the sentences that we're talking about are only about people, we're just going to say, look, just keep in mind we're only talking about people. So when we say for all of x, we mean all people. Right? So limiting the universe of discourse can sometimes serve to make things a lot more simple. Sometimes you don't need to limit your universe of discourse. Sometimes you do, and that's depends on context. All right, so let's get to formalization. Now notice this sentence is a little bit ambiguous to begin with. Okay, so it's ambiguous between two possible readings, one of which is more natural than the other. So you could say something like, well, look, there's somebody out there for everybody, right? And one thing you might mean by that is that there's some particular person, right, who is the perfect match out there for literally everybody else, right? There's one specific person who's the right match for every other person. That's one thing you could mean. You probably don't mean that. The more natural reading is, look, there's somebody or other out there for everybody, right? So given any given person, some other given person is a good match for them, right? That's probably what somebody meant when they said there's someone out there for everyone, okay? And so what we don't want is we don't want to say there exists an X such that for all of Y, X is for Y, okay? That's that first reading where it says, no, there's one person who is a good match for anybody, right? That's probably, again, it's not what we meant. Rather, we mean this. We mean that for all of x, right, there exists some y such that x is for y, right? And so for everybody out there, there's somebody or other that's a good match. Not that there's somebody that's a match for everybody, right? And so keeping in mind of which of these quantifiers to put first and which to put second, sometimes it'll really sort of bend your mind into knots. But again, you'll have to sort of phrase it out into common English and think about it until it gets a little bit more automatic.